Hey, welcome back, Math Nines. We're going to dive into 2.2 now, the zero exponent law and powers of 10. So first, let's explore the zero exponent law. So I'm going to give the law right off the bat here and say anything raised to the power of zero except when a is zero. So a cannot equal zero. We're not going to deal with zero to the zero. We're always going to get one. And it's a strange concept. You're saying, well, it, a exponent is repeated multiplication. If we're raising it to the power of zero, it means there's no repeated multiplication. So shouldn't you just get a is where our instinct goes? But I'll explain this as quickly as I can and as simple as I can, actually, just with a basic pattern. So we're going to go down into this chart here, and it's going to help to make sense of this zero exponent law. Um, Starting at the top here. So we have 3 to the 5. So review of last day, 3 to the 5 is saying my base is 3, and it's being repeatedly multiplied by the exponent 5 times. So this means 5 times I'm going to multiply 3. So my base is 3, and my exponent says multiply the 3 5 times. And again, we're not using the multiplication symbol, we're using brackets. And if I were to evaluate that, if you were to calculate that, you'd get 243. So remember, standard form is just, well, hey, what does this equal when you multiply it all out? Next one here, I'm doing 3 to the 4. So I'm going to start moving a little bit faster here. And if we do 3 to the 4, we're actually going to get 81. And let's do 3 to the 3. And we can see each time I'm decreasing the number of 3's and multiplying them out. Finally, 3 squared is just 3 times 3, that's 9. And then a single 3 all by itself is just 3. And now if we follow this pattern, right, every time we are subtracting 1 on the exponent, okay? And so that means this last one should be 3 to the 0. Now, this says NA. We essentially cannot represent this in repeated multiplication because, well, nothing's being repeatedly multiplied. The 3 does not exist. But what I didn't say was there's actually a 1 sitting in front of all of these. Okay? And so there is a 1 here that's not being repeatedly multiplied with anything. But let me prove this a little bit better with a pattern. So if I go from here to here, what these values are, I'm actually dividing by 3. 243 divided by 3 is 81. And 81 divided by 3 is 27. And if we keep doing this, divide by 3, well, what's the last one? If I take 3 and divide it by 3, of course, 3 divided by 3 is 1. So we can repeatedly multiply, but we can also go backwards and repeatedly divide. And this is how we can see, oh, if I have something raised to the power of 0, it's going to equal 1. And this doesn't matter if it's a 3, a 10, a negative million, 257,605. If it's raised to the power of 0, you're always going to get 1. So let's take a look at 4 quick examples and see what happens here. So whatever the 0 is attached to is going to turn into a 1. So since the 0 is attached to the 4, there's no negatives here to worry about. We're going to get 1. Now we do have a negative 4 as the base here, but the 0 is attached to everything in the brackets. So everything in the brackets is going to go to 1. So it doesn't matter that there's a negative here, okay? It doesn't matter if we have decimals or fractions. If whatever is raised to the power of 0, whatever it's attached to will become a 1. Now, in this case, we remember from last lesson, the 0 is only attached to this 4. So there is a negative out front here. So you can think of this as negative 1 times 4 to the 0, which of course 4 to the 0 is just 1. And negative 1 times 1 is negative 1. So just be careful if there's a negative not attached. Finally, we do have some decently big numbers here. Negative 32 times 41 divided by 254. And BEDMAS says, hey, do brackets first and follow your order of operations. But we know after I finish these brackets, right? Once I simplify it down to a single number, whatever that is, I'm going to be raising it to the power of 0. So I don't actually care what any of this equals because no matter what it is, I'll be raising it to 0, which is 1. Okay, so that's the zero exponent law, is basically in about, I think, less than 5 minutes there. Let's start exploring actually something really applicable, especially in science, are powers of 10. Now, this is really important for the metric system, of course. It's entirely how the metric system is built when we're talking about meters and kilometers, or millimeters if we're talking about distances, or same thing with liters with volumes, or grams with masses. So let's take a look at what's happening in this pattern, what's been filled out for you so far. So I'd like you to think to actually start at just one, starting initially at one. And we can see this pattern here. We're going to see that, well, that's got to be 10 to the 0. And as we move up, we're multiplying the 1 by a 10. So if we multiply by 110, we get 10. We multiply by two tens, we get 100. By three, 1,000, and so on. But there's something kind of that's really helpful here when we look at this all, is anytime we take a 10 and raise it to an exponent, a positive exponent, the number of zeros, okay, following the 1 is equal to the exponent. So if we count in 1 million here, I have 6 zeros. Well, that's 10 to the 6. So 6 zeros matches an exponent of 6. 5 to 5, 4 to 4, and so on. Now, if we keep going in this direction, okay, we're getting all the way down to 1. Well, what happens if I continue to divide by 10? Well, if I divide 1 by another 10, I'm going to get 1/10, which we write as 0.1. That's 1/10, okay, 1/10 of 1. And this, again, is the first time we're going to see something new, not just the zero exponent, but now we have a negative exponent because every time we're subtracting 1 as we move down this column. So 10 to the negative 1 represents division by 10. Division by 10 is what's being represented by this negative 1. And if we do it again, we'd get 1/100th. I believe it's 1/100th. Okay, which we divide again. It's actually going to move our decimal one more over. Okay, and that's going to be 10 to the negative 2, or dividing by 10 twice. If I take 10 or 1 divide by 10, I get 0.1. Divide by 10 again, I get 0.01. And you're going to see this pattern now. You can try it in your calculator. If I go one more, I'm going to get 1,000th, which moves me over again, which is 10 to the negative 3. And let's just go one more for fun. 1/10,000th is going to move me over one more. So we're getting smaller and smaller and smaller when we divide by 10, which makes sense. Every time you divide by 10, you're going to get 1/10 of what you had. And so all of these have a bit of a pattern. You can think of it this way, is the decimal places. So the number of decimal places this time, you could think of it as the zeros if you count the 0 in front, but it's better to think of it as decimal places, and we'll see why in a second. But the number of decimal places is equal to the exponent. It's equal to the exponent. Now there's something really unique here I want you to see, is that there is a decimal right here for 1. Okay, we don't write it, but it's there. And every time I divide by 10, my decimal moved to the left. It went over 1, it went over twice, 3 times, 4 times left. And every time I multiplied by 10, I actually am moving the decimal to the right. So it's over right, over again, each time I'm multiplying by 10. So a great way to think of 10 is when you multiply 10, you move the decimal to the right. Okay, get 10 times bigger. If you divide by 10, you move left, you get 1/10 of what you had. Flip over the page and let's learn, how do I apply these powers of 10 in a thing called scientific notation. So this notation, as the name suggests, is extremely important in science. Okay, you use it a lot in chemistry, in physics, in earth science. Basically, it's really handy for writing very large or very small numbers. Okay, and it will look something like this, where there's always a number m times 10 to the something n, and this m has to be between 1 and 10. So it'll be like 2.4 or 9.5. It just will never be um, great equal to 10 or greater, and it always has to be 1 or greater. Okay, so it's in between 1 and 10. That's what these less than or equal to and less than define. But let's actually take a look at what's actually happening here. So we want to write these quantities in scientific notation. So the best way to learn this is, let's do 6 examples. So this is a huge number. Okay, this is 10 billion, and there is a decimal currently. It's sitting right there. But in scientific notation, we actually always want to move our decimal to the leftmost non-zero digit. Okay, these are all zeros except for the 1. So we're going to move this all the way beside the 1. So we need to count how many times we move it, and that's by digit. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we moved it 10 to the left here. 10 left. So now we have a new number because, well, I put the decimal there, but I can't just say, okay, my answer is 1. That doesn't really make any sense. I have to say, well, where did all these zeros go? And we represent that by saying, well, that's same as saying 10 to the 10. Because if I took 1 and multiplied it by 10, 10 times, 1 times 10 times 10 times 10, 10 times, it would move the decimal way, it would take this decimal, right? Because there is one right here, right now, and move it back to where it was. So we purposely moved it this way, and we have to account for all of those zeros by saying, well, that's the same as saying times 10 to the 10. So here's all my zeros in the 10 to the 10 piece, right? And then here's my actual number. Let's take a look at something that's not 1. This is 3 million. Again, my decimal's here. I'm going to move it 1, 2, 3, 4, 5, 6 right here, okay, to the right of the most leftmost non-zero digit. So this is 3. Now we don't normally write it, but the decimal is right there now. And I have to represent all these zeros, all these place values by saying, well, you take that 3 and multiply it by 10 6 times because we moved it 6 to the left. And you could try that in your calculator. I'd like you to go 3 times 10 6 times. So take 3 times 10 times 10 times 10 times 10 times 10 times 10, and you should have 3 million in your calculator. Okay. Next, let's try another one. We have a couple numbers this time, but still it's the leftmost non-zero digit. So 1, 2, 3, 4, 5, 6. Do not stop here. You have to go one more to get it right there to the 4. Because remember, it has to stay less than 10. 43 would be too big. So now I have a new number, 4.3, and we never write the trailing zeros because we need to represent all 7 of these place values by saying, well, that's the same as saying 10 to the 7. Again, if I multiplied 4.3 times 10 7 times, I'd be back to 43 million. Let's try one with a few more digits, like 835,000. Again, let's move our decimal 1, 2, 3, 4, 5. So now I have a new number of 8.35. And then how many times did I move it? 10 to the 5. All right. What about really, really, really small numbers? Again, we can actually see the decimal this time. We always want to move it again to the leftmost non-zero digit. These are all zeros until you get to the 1. So let's move it 1, 2, 3, 4, 5, 6, 7, 8. I want to put it right there. Okay, so that time we went 8 to the right, we have a really, really small number. So our new number, we moving the decimal, is just a single 1 again. The decimal is technically right here. You don't have to write that, but I want to emphasize where it is now. And then that's the same as saying times 10 to the -8 this time. Well, why is it negative? Because remember, this represents repeated division. So if I took 1 and divided by 10 8 times, I'd be back to 0.0000001. Okay, so we use negative exponents to represent repeated division or really, really, really small numbers. Let's try one more. Again, I want to move my decimal to the leftmost non-zero digit, which is 4. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 this time. So my new number is 4.32. Don't have to write all these zeros because I'm going to represent them with 10 to the negative 10 because we moved it 10 to the right. So now we have a really small number represented in scientific notation. And let's take some real world examples and go the other way. Like all things math, you learn to do one way, you have to learn to reverse it. So population of world I know today is greater than 7. I believe it's over 8 billion now. But let's take this and represent it as the real number, not 7 times 10 to the 9. Let's write it in the long way with all the zeros. So the way to do this is you take the current number that we have in scientific notation, which is 7, and the decimal's right here. And the 10 to the 9 says, okay, move the decimal 9 to the right because this is going to make it bigger. That makes sense. I'm multiplying by 10. Every time I multiply 10, I move the decimal 1 time. So let's move it 9 times to the right. So this is the same as times 10 times 10 times 10. That's 3. And then times 10 times 10 times 10. That's 6 times 10 times 10 times 10, that's 9. So then redraw your decimal, and then this little wave here, put a 0 in every little opening. So I've taken my decimal, I moved it 9 to the right. Now this is the work. Actually give a final answer that shows the number clearly. So 7 followed by 9 zeros. And if we put the commas in, remember commas always go every 3 digits from right to left, we see now clearly that this number is 7 billion people. Okay, let's do another huge number, the distance to the nearest star, other than this is distance from the sun, our sun, to the next nearest star, because of course the sun is a star by definition. So we're going to start again with the number given, which is 3.99. And this fifth 13 says, how many times do I got to move it to the right? So we're multiplying by 10 13 times. So move it to the right 13 times. So I'm going to go 1 between the 9s, 2, and then 11 more. So 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I've gone all the way over here. Here's my new decimal. Fill in all my missing zeros in my wave. And this number is huge. And now that's my work. Let's rewrite it. So 3990000 0000000. So careful writing them down. Let's put in my commas and let's see if we can actually say this number. Okay, this is huge. So this would be 1,000 here, 1 million here, 1 billion here. So that's 900 billion. So the next one would be 39 trillion 900 billion is how big this number is. And because there's context, please don't forget your units. So that's kilometers. That's pretty far away. How about something really tiny like the diameter of a really small virus? So I'm going to write my number over here this time, 1.8, because I know I have to move my decimal to the left because of this negative exponent. It's a really small number. So I'm going to move it to the left 5 times. 1, 2, 3, 4, 5. So now we're going in this direction. We rewrite our decimal and fill in all of our missing zeros. And let's rewrite it. So 0.00001 8. So we've moved the decimal 5 to the left, and here's the actual number, or millimeters, of the diameter of the smallest known virus. Last one, mass of a dust particle. Super light. So this is a really, really, really tiny number. So again, I'm going to start with 7.53. And this -7 is telling me move it left 7. So carefully count 1, 2, 3, 4, 5, 6, 7. Redraw your decimal, fill in your zeros. Now this really tiny number, we can finally represent it as 0.00000. How many do I got? Always be careful. Okay, so 6 zeros there after the decimal, and then 753. All right. So super duper quick recap. Let's go back to the top. We learned what the zero exponent law, which means anything raised to the power of 0 is 1. And then we did a few examples of that. So careful when the negative is not attached, okay, to the 0, but anything attached to the 0 becomes 1. Then we looked at some patterns with starting with 1. If we multiply by 10 a bunch of times, or if we divide by 10, what happens to the decimal place? Okay. We applied that basic understanding of powers of 10 to allow us to do something called scientific notation. So we could write really big numbers like A, B, C, and D into scientific notation. They'd be shorter. And really tiny numbers into scientific notation. So the biggest thing to recall here is when we have big numbers, we have a positive exponent because we're multiplying by 10. And when we have really tiny numbers, we have a negative exponent, which represents division by 10, which makes them really small. Finally, we went the other way and we learned how, okay, what if something's in scientific notation and I want to write it out in the long way? Okay. And we do that by simply starting with the number in front that's given to us, and then the exponent tells us which way to move our decimal, and then rewrite. So we did that making really big numbers and two really small numbers. That concludes 2.2. We'll see you next time. Have a good one.